This is example 12.4 in Discovering Design with Chemistry. And I think I might like this even less than having to draw 3D molecules or the Lewis structures because I just don't like drawing. But don't worry, we only have to do it for this chapter. We don't have to keep drawing these batteries for the whole rest of the course, so just a couple. A galvanic cell is powered by the following reaction. Draw the cell, labeling the solutions on each side, the anode and the cathode. Also indicate in the direction in which the electrons will flow in the cell. So let's go ahead and label all the different oxidation states so we can see what's happening to help us know where those electrons are traveling. So the oxidation state for copper right here is 0. And hello. 0. For the silver, it's 1 plus, and then the copper is 2 plus on this side, and the silver is 0. So you can see what's happening. So the copper went from 0 to 2 plus, so it was oxidized. And to help me remember which one's which, I say an ox and red cat. So this is oxidized. That means it's the anode and ox. And then the other one, the silver, went from a 1 plus to a 0. It went down in number, so it was reduced. And I use my little thing again, red cat. So this is the cathode. Now we can get to drawing. So let's start by drawing our containers. So here's our 2 containers, and typically the anode's going to be on the left, so we're going to put the anode here. It's negative, it has an N, that's how I remember the anode is negative. And the cathode is going to go on the right. The cathode is positive because it has a T in there. That's how I remember the cathode, it's the positive one. Alright, so the one that is in the anode is the copper, so let's go ahead and start. And copper in this equation starts on as a solid. So this is actually, let me get a different color so it doesn't combine with my other things. This is the copper cathode. On the other side, we also have some type of, oh, why did I say cathode? That makes no sense. What is wrong with my brain right now? Sorry, guys. It's an electrode. All right. I'm going to blame it on my cold. Okay. The other side, we don't have anything on the product side that is on the reactant side that is solid to go with it. So this is just an electrode. Doesn't matter what it's made of. As the reaction happens, we do get some solid silver. So eventually silver will get plated on the outside of this, but it doesn't really have to be made of silver. All right, so next, let's label a few other essential pieces. I'm going to change colors a little bit to make this easier to see. So this is going to be our salt bridge. And it didn't ask us to label anything about that. I watched a few videos online of other people doing this, and some people actually label what's happening in their salt bridge, but we're not going to label that. And then we're also going to label, let's pick a different color. We're going to label the flow of electrons. This is why I like to put the anode on the left and the cathode on the right, because they're going to go, oh wow, that was a terrible arrow. See guys, that's why I don't like drawing. All right, so our electrons are moving in this direction. All right, and then the other thing we need to know is about the solutions it asks for. So in this solution, as that reaction happens, we're going to end up with our copper ions, and then on the other side, this solution contains, I'm just going to write with because contains is too long, our silver ions. And as those little Ag pluses get their electrons that are coming across that green line that I drew, that metal wire, they will become just silver and it will start plating in solid form on that electrode. But they're in the solution. And the same thing on the other side, but the opposite, that copper that's solid, as it loses electrons, for every 2 that loses, it will turn into copper 2+, and that will be in aqueous form floating in that solution. And the salt bridge keeps everything moving so those electrons don't just get all piled up on the other side. So this is our answer. Now, in the book, if you look at the picture, in my book it's page 372. I'm not sure if yours is the same for your edition, but it points out a few things in the example. And he colored his water in the anode side, or not water, but the solution, yeah, I guess water, blue because he knows that copper 2+ ions are blue. I did not color mine blue because I didn't really want to deal with it. I guess I can, probably should indicate that there's solution in here. There we go. I'm not coloring that blue because that would take me too long with this tiny little pencil thing. And then he also colored his copper electrode like sort of an orangey brownish, like a copper color. I did not color mine. It doesn't have to be colored. The important thing is that you got everything drawn and labeled, even if it's a kind of terrible drawing like mine is. The idea is that you have to have everything labeled, not that it has to be the right color, but you can color it if you like. And then another thing that's pointed out in the example, and you can read this yourself in the book, is that copper is changing into copper ions here. And in the galvanic cell that you made in an experiment, the copper ions became copper, and so that worked as the cathode. But in this case, the copper is on the anode side. And it can be both because it depends on what it's paired with. Aluminum doesn't hold on to its electrons, so in our experiment, the copper was the stronger one, so it like pulled the electrons. In this case, though, silver holds on to its electrons more strongly than copper, so it pulled those electrons over and copper just let them go. All right, let's look at our second one. Oh, wow, it's way over here. Okay. A galvanic cell is powered by the following reaction. Draw the cell, labeling, blah, blah, blah. Same thing. Okay, so let's start by labeling this, and then we'll draw the cell and label all the pieces it wants us to label. So let's look at our pieces real quick. We have a 2+ charge on this one, a 0 charge on that one. This one has a 2+ charge, but this is a polyatomic ion, so this 2+ charge applies to the whole thing, but each Hg is actually going to be a 1+. It's just that we have 2 of them because of that little 2 right there. And then zinc is just one thing, so it's going to have 2+. So let's look at what's happening with our things. So our Hg started at 2+, and then it went to 1+. And you kind of have to write it out to see that, because when I first looked at this, I was like, oh, mercury is 2+ here, it's 2+ there. And it wasn't until I looked at it closely and was looking at the example, I'm like, oh, wait, that's Hg2. That's like a homonuclear diatomic molecule. And so that one, whatever, it's, got 2 in there. So the overall charge of +2 is what those 2 atoms that are combined in that molecule have together. So each individual atom is just 1+. All right, and then our zinc is much easier to see. It's way more straightforward. All right, so let's look at this real quickly. So which one went down in number? Mercury did. This one was reduced. And so that means that is our cathode, red cat. And then the zinc went up, so that means it was oxidized. And ox, that is our anode. All right, now that we've got our pieces of information, let's draw. I'm going to change color because I want to use the blue for my water. All right. All right, so here's my solution in the 2. And I'm going to go ahead and draw an electrode in each. So here's an electrode in this one, and here's an electrode in this one. All right, so do we have anything solid in the reactants? Yes, the zinc is solid. And let me go ahead and label anode and cathode. Again, I like to put the anode on the left, the cathode on the right, because then as I draw my little electrons coming across, I can have them going like in the same direction that I read, left to right. Okay, so in my thing, zinc is on the anode side. It's being oxidized, and zinc is solid, which means that this electrode right here is a zinc electrode. Writing on a computer screen is really hard. My handwriting, I promise, is not like this bad in person. On paper, I mean. All right, on the other side, we know that the mercury is on the cathode side, but the mercury is aqueous as a reactant, and so this is just, we can just label this electrode because we don't know what it's made of. Now in this solution, let me scoot this over just a little bit. We can label this as the solution that contains the Hg2+ and also the Hg2 2+. The ones that are there at the beginning, the ones that have a 2+ charge, and the ones that as they receive an electron, they individually end up with just a 1+ charge and then come together, I guess. And so that's that solution. The other solution is over here. Let's get rid of that line. This solution is going to contain the zinc 2+ ions that are floating around as the zinc loses its electrons to the other side. And then the last thing we need to draw, let's make it green. So this is, let's make a little path for it. This is our salt bridge. All right, so that's all the pieces we need. Let's check the instructions. We drew the cell, which is like the whole thing. We labeled the solutions on each side. We labeled that the left one was solutions with zinc 2+, and the right one was solution containing Hg2+ and oh shoot, yeah, must spelled that one wrong. Let's fix that one. Hg2 2+. There we go. Good idea to check your work. We labeled the anode and the cathode, and then we also drew the salt bridge because it didn't tell us to do that, but we know that that is part of that draw the cell part. We have to have the salt bridge in there. We have to have the electrodes in there, and they need to be labeled. If it's an electrode like the zinc one that we know it's solid, we can label it. Otherwise, we just write electrode. And then we indicated the direction in which the electrons would flow in the cell. All right, I think that's the end of this example.